product of two numbers is 30240. HCF is 6. So 6A and 6B. Now I'm going to go to discussing this. The HCF of two numbers X and Y is given as H. Then the two numbers can be written as HA and HB. The most important criteria here is that A and B have to be co-prime. So once you have extracted the HCF from two numbers, then what you are left with, there cannot be anything in common. And very simple funda, but you have to get this right to approach all of these questions. And so if you have two numbers X and Y which can be represented as HA and HB, HCF is H. What is the LCM of these two numbers X and Y? LCM of HA and HB in the general context. H times A into B. When two numbers are HA and HB and HCF is H, then A and B are co-prime and LCM has to be H into A into B. So whatever the HCF, extract that. What you are left with, that has to be co-prime. What you are left with, multiply those two and then the HCF, then you'll get the LCM. And so once you have done this, then this question becomes very routine. And so 30240 is H square AB, 2 power 5 into 3 cube into 5 into 7. The HCF is 6. So we're going to knock off 6 twice over from this. And so A and B are co-prime. So we know A into B is 2 cube into 3 into 5 into 7. We have knocked off 6, 2 into 3 twice over. Or we have knocked out 2 square into 3 square. And so 2 cube into 3 into 5 into 7, that has to be broken as a product of two co-prime numbers. And in how many ways can this be done? 2 cube into 3 into 5 into 7. We want to break it as a product of two co-prime numbers. I've given the answer there, but I want you to tell me the answer still and give me the method as well. What is the method for this? 2 cube into 3 into 5 into 7. How do you break this as a product of two co-prime numbers? I had explicitly planned to not do this elaborate part. See here, you have 4 primes, 2, 3, 5 and 7. And so think about it like this. I'm going to break this as two boxes. The two boxes have to be co-prime. And so if I put a 2 here, then all 3 2's have to go in there. I cannot put 2 power 1 here and 2 square here. Then the numbers won't be co-prime. And so I want the two numbers to be co-prime. I want to break 2 cube into 3 into 5 into 7 into 2 pots such that they are co-prime. They shouldn't have anything in common. And so if I put 1 2 here, then all 3 2's should go here. So effectively, pardon my digital writing. So 2 cube is one block. You cannot break this as 2 power 1 and 2 square or 2 square and 2 power 1. So whether it is 2 cube into 3 into 5 into 7 or 2 power 100 into 3 power 500 into 5 power 600 into 7 power 100, it doesn't matter. It is same. The method is identical to breaking 2, 3, 5, 7. And so now how would you break 2, 3, 5, 7 into 2 pots? Each of those numbers 2, 3, 5 and 7 has 2 choices. It can go into first box or the second box. It can go either here or here. So 2 has 2 options, 3 has 2 options, 5 has 2 options, 7 has 2 options. So there are 2 power 4 ways of breaking this. Right? But in that, the 2 into 3 in one box and 5 into 7 in the other box will get counted, and the opposite way will also get counted. So if you do this approach, you know, effectively double counting. So it's not 16, it's only 8. The shorter formula is what is being given there. There are n different primes. The number of ways of breaking that number into product of two co-prime numbers is 2 power n minus 1. That's the formula that's being given here. You should know this formula. You should know the funda behind this formula. Remember again that the power of these primes does not matter. Only how many primes are there that matters. Whether you are worrying about 2 into 3 into 5 into 7 or 2 power 5 into 3 cube into 5 square into 7 power 5, it doesn't matter. And there are 4 primes. They can be broken as product of two co-prime numbers in 2 power 3 ways, 8 ways. Why so? That's what we discussed. We don't take each prime and put it into one box or the other. And so there are 16 ways of doing this. But in this 16, x into y will get counted, and so will y into x. Effectively, we are double counting. So it is 16 by 2, 8 ways totally. Right. I'm going to go to the next one. Again, give this a go. A minute, minute and a half. Very similar to the template that we've already seen. Right. The LCM is not 1, it is L. And so H plus L is 105 and H is greater than 1. Effectively, we are being told that the numbers are not co-prime. We're looking at two numbers whose HCF is H, LCM is L. And we know that the numbers are not co-prime. We want to see how many such pairs of numbers are possible. Same template, if you're given a HCF, assume numbers to be HA and HB. What will the LCM be? What is the condition for A and B? then go back to solving this question. Again, same template. I'm just going to broadly outline the method. Those you've got the method, go ahead and plug it in. Those you're stuck for the method, I'm going to assume the numbers is HA and HB. The moment I assume the numbers is HA and HB, should take into account that A and B are co-prime. And so A and B are co-prime, the numbers are HA and HB. LCM is H into A into B. So we have H plus HAB equal to 105, or H times 1 plus AB is 105. And we know H is not equal to 1. So figure out what possible values H can take and then simplify after that. What values can H take? H into 1 plus AB is 105. H can be 3, 5 or 7. So H can be 3, 5 or 7. Why not 15? Can be 15. It can be, it is H into 1 plus AB. Can H be 15? Can H be 105? 35? H cannot be? H cannot be greater than LCM. Okay, so it cannot be 105. Correct. 15 into 7 is the total. So HCF is 15, LCM is 90. Why is that not possible? You're saying H into 1 plus AB is 105. So H into 1 plus AB is 105. So HCF is a factor of 105. It cannot be 1. That much we know. Because they've told us that the numbers are not co-prime. So they're not co-prime. That much we know. So H is not 1. So H could be 3. In which case 1 plus AB would be 105 divided by 3. 105 by 3 is 35. So 1 plus AB would be 35. H could be 5. In which case 1 plus AB would be 21. H could be 7. In case 1 plus AB would be 15. Can H be 15? Yes. Because 1 plus AB would be 7. So A into B would be 6. Can H be 21? 1 plus AB is 5. AB would be 4. H can be 35. 1 plus AB would be 3. AB would be 2. So you'll have to evaluate all of those possibilities. So give that a go. I'm going to stop here. So I'm going to pause at this point. What you've got so far is H into 1 plus AB is 105. And then build from there. So you can factorize 105. One of the factors can be H. The remaining is 1 plus AB. Important caveat here, HCF cannot be greater than LCM. So keep that in mind. So if HCF is 35, LCM is 70, you might get some possibilities. Right? But you cannot have a possibility where HCF is 70 and LCM is 35. That's ruled out. Right? So keep that in mind. So HCF 35, LCM 70 might be still possible. Then what are the two numbers that could still be a possibility? Right? So try out all those possibilities. It's 105 is heavily factorizable. So it's not likely that you'll get a question with such a large number. But this template is very much common. Given that sum of HCF and LCM is equal to a certain number, find how many pairs are possible. Given product of two numbers and their LCM, how many pairs are possible. Product of two numbers and HCF, how many pairs are possible. That is fair play. That is a reasonably common question. All works of the template, the numbers can be assumed as HA and HB. LCM is H, AB. HCF is H, A and B are coprime. One standard framework for all of these questions. Right? So HCF is H, numbers are HA and HB. Straight away A and B are coprime. LCM is H times A into B. And so use just these four and form an equation at the end of that. After that, you're doing a routine question where product of two numbers is 105 or sum of two numbers is 37. Then you're simplifying after that. The caveat that you need to remember, keep in mind, is that A and B are coprime. Once you extract the HCF from two numbers, and what you're left with cannot have anything in common. After that, you still have to do it rigorously, find all the variants. So in that rigorous part, this question becomes too long. Lots of different elements to consider. Therefore, it is tough. It's probably a question that's going to take 3, 4, 5 minutes to solve. Therefore, you won't find a question like this. But the template as such is fair play. That's not rocket science. HCF plus LCM is 105. Find total number of possibilities. Very regular question. You will get questions like this, especially given that HCF is not equal to 1. So given that caveat. So 105 can be written as 1 into 105, 3 into 35, 5 into 21, 7 into 15. Right? HCF cannot be 1. That's given in the question. HCF cannot be 105. That's a given. Then AB would become 0. That's not possible. So HCF can be 3, 35, 5, 21, 7 or 15. And all 6 are possible. For each of those 6, we'll get a value for AB. So 6 values of H, 6 values of AB. That's not enough. That doesn't mean there are 6 pairs possible, but given an AB, there could be multiple pairs possibilities for A and B. If A into B is 6, then AB could be 1, 6 or 2, 3. And so worry about that also. Again, I'm going to pause. Worry about that. Find the whole solution. Then we'll go to the next question. This is possibly a tougher question than what you'll see, but wonderful question to practice. You get this right rigorously, where you say, let me take HCF is 3, AB is 34. 1 into 34, 2 into 17. HCF is 35, AB is 2, 1 into 2. Work each of those numbers and then add all the possibilities up. You do that for one question, then this template kind of gets set in place. So take 1 more minute if you have to, but get this right. And so we're going to take HCF is 3, AB is 34, HCF is 35, AB is 2, HCF is 5, AB is 20, HCF is 21, AB is 4, and 2 more possibilities. Each of those for a given AB, how many possibilities of A and B exist? Remember, the final condition you still have to keep in mind is that A and B are coprime. And so don't forget that. Then you'll get more possibilities then. In number systems and geometry, you need to be rigorous, especially number system. What I mean by rigorous is it's not enough to get the funda and idea. You need to make sure that you're counting well, you're ticking all the boxes, worrying about phrases like non-negative, positive integers, natural numbers, whole numbers, distinct, not necessarily distinct. Each of those adjectives means something. And so don't gloss over the detail in the question. Details matter. And in this question, you should have accounted for all ways of breaking 105. You should have ignored 1 into 105, taken the 3 ways of breaking it, worried about both ways. What do I mean by that? Think of writing it as 5 into 21 and 21 into 5. HCF is less than LCM, but HCF need not be less than 1 plus AB. And so HCF of 15, 1 plus AB of 7 is possible. And then you've got those 6 possible values of HCF. You'll have to now worry about the 6 values of AB and then break it down. And in that, you should ignore 2 into 10. When AB is 20, AB can be written as 2 into 10, but you cannot take 2 into 10 into account because 2 and 10 are not coprime. And if the HCF is given, You're breaking two numbers as HA and HB. A and B have to be co-prime. So 2 into 10, you cannot afford to have counted. So keep that in mind. So that's why that possibility has not been written down. When AB is 20, then A is 2, B is 10. That possibility you should not count. Because if you count that, then the HCF jumps. It's no longer 5, it will become 10. And so that becomes an issue. The moment you extract the HCF, you're going to be left with co-prime numbers. That's vital. So you have to maintain that rigor throughout. We finally get to 10 pairs. Right. Tough question, not because of funda, but because there are 10 pairs. You get a question like this, they'll make sure the answer has 4 or 5 where you can list down easily and do it quickly enough. But it's a very useful question because you know the full template and you have to be careful at every step with the math. Each funda you should know. Just a quick recap. Two numbers A and B have a HCF of H. Then we can assume A is Hx, B is H into Y. Straight away you know that HCF of X comma Y is 1. X and Y have to be co-prime. If they're not co-prime, the HCF will no longer be H. If we take everything in common between A and B, put it in H, then remaining, they cannot have anything in common. LCM of the two numbers is H into X into Y. Extract the HCF, take the remaining two co-prime numbers, multiply all three, you'll get the LCM. Try this one. The first two questions were tougher. This is far simple. This is very routine. Plug in the formula, it should be done. You're basically looking at odd factors, so we cannot have 2. So 3 power 7, 10 power 4, 5 cube, 8 into 5 into 4. A plus 1 into B plus 1 into C plus 1. So you cannot have any 2. So forget the 2. What you're left with, that's all we need to combine. Is that right? So forget 2 power 5. We're effectively dealing with 3 power 7, 10 power 4, 5 cube. So 7 plus 1 into 4 plus 1 into 3 plus 1. Is that right? It's not right. And you cannot plug in that formula unless you have prime factorized the damn thing. And so worry about that. It's a kind of classic error you can walk into because you're doing things in a hurry. And you're doing it in an exam context. You say no 2's in it, remove 2 power 5, plug in the formula, I'm done. This number is a natural number, but what we have been given is not the prime factorization. And the starting step for a lot of number theory is prime factorization. So take this number and then say, look, I'm not plugging any formula in here. First, I'll prime factorize this thing. So prime factorize that, get that going, and then simplify that. It's a very routine question, but with one obvious juicy wrong answer, which is 8 into 5 into 4. Don't find that answer. And so be very careful. Every time you walk into one trap or the other, you need to place a mental cue. So look, I'm not making that mistake again. And so a lot of times I find students operating in a state of frenzy when they go to mocks. And so you need to be quick. You need to cut down your time between questions. You need to cut down your concentration lapses. But if you're saying, look, every question I'm going to do, bam, 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 then you'll commit error after error after error. And you'll have I'm sure quite a few of you have seen this experience where you say that I've done this mock, I look at question number 21, I look at it and I know the answer choice is C. For some reason, my answer key says that I marked B. I cannot even imagine how I marked B. And that frequently happens, that basically because you're trying to operate at a speed higher than you can cope with. At a question to question level. And speed in mocks is about two things. One is about question selection, two is about intensity, not letting your concentration drop. Nobody can suddenly overnight read quicker or multiply quicker. If it takes you X seconds to do 83 into 45, it'll take you X seconds. If it's going to become quicker, it's with lots of practice. Suddenly in a mock setting, you cannot multiply quicker. And so don't try to speed up everything that you do. Then you'll go into a frenzy mode and miss detail. But I can imagine this question having a 25% error rate in the exam because you've glossed over the fact that 10 is not prime. And so don't rush at a question level. You see a question, know the method, plug it and get the answer, go to the next one. You should be intent, you shouldn't have concentration drops. That is important. But you cannot try to do everything quickly. It won't work. Nobody can do that. There's no such thing. You cannot suddenly do everything. You can't do that. You can't suddenly look at a question and say this is the answer, I'm plugging it in. It won't work. So at each question level, operate at your natural speed. Don't try to randomly ramp up. That will lead to makes your error rate goes out of whack. I know for a fact that this question in mocks will get a gigantic error rate, and almost everybody knows that you need to have the prime factorization to plug in that formula. Fine. So, but in the exam context, you're trying to operate and cut every corner. Don't. You need to be intense. You need to be relaxed. You need to balance both of those. Fine. So don't rush and make that mistake. If you don't make that mistake, it's a very routine question. Fine. So this can be prime factorized finally as 2 power 9 into 3 power 7 into 5 power 7. Ignore 2 power 9, 3 power 7 into 5 power 7, 8 into 8, 64. Try this one. The factors of 2 power 5 into 3 power 7 into 5 cube that are multiples of 600. We want numbers that are factors of the larger number, which also happen to be multiples of the smaller number. Just for the record, all of these are regular questions. You will get questions of this level of difficulty merrily. And you shouldn't be at a place where you're nailing them down in a minute and a half. Just plug it in, you're done, you're writing the answer and going on. And so none of these questions is particularly tough. Question number 2, where it added up to 105. The template is par for the course. But since there are 10 possibilities, it's unlikely. Your exam will have an answer where there are 4 or 5 possibilities. You can list them down quicker. Any multiple of 600 is going to be of the form 600k, where k is a natural number. So 600 into k is a factor of this number. So find prime factorize 600, and this question becomes far simpler. Any 600k that's a factor of this number, that means this number by 600 will also be a multiple of k. So effectively, we are saying if you call this as n, find n by 600 and find number of factors of n by 600. That's it. So 2 power 5 into 3 power 7 into 5 cube, divide that by 600, find number of factors for that number. So this number has a factor that's a multiple of 600. So the factor will be of the form 600 into k, or effectively k is a factor of this number by 600. Find all possible values, we're done. So 2 power 5 into 3 power 7 into 5 cube divided by 600. That will give us 2 square into 3 power 6 into 5 power 1. Find the number of factors, which is 3 into 7 into 2, we're done. The number of factors that are multiples of 600. So any multiple of 600 is 600 into k. That number is a factor of n. That means n by 600 has to be a multiple of k. So find all factors of n by 600, you're done. Yeah.
Will we add 600 also?
That will be included in this. So if you find number of factors of this number, 2 square into 3 power 6 into 5 power 1, one of those factors will be 1. That is included in this. So if all the factors that you find here, your answer is each of those into 600. So 600 will get included. So if I list all factors of 2 square into 3 power 6 into 5 power 1, our answer for the exact factors, each of these factors into 600. One of those factors is 1. 1 into 600 will give you the factor. So that will get counted. This again is a variant of the same formula. So if n is of the form p power a into q power b into r power c, the number of factors is a plus 1 into b plus 1 into c plus 1. That we know. When number of factors formula, you should also know the funda for that formula. Why do we have that plus 1? Why do we multiply? What is the idea there? But once you know that formula, all of these are based on mild variants of that formula. Once again, this is wonderful 10 sitting there. Be wary of it. It's not prime. We want to find the number of factors of 2 cube into 5 power 4 into 10 square into 3 cube that are perfect squares. We're going to take this prime factorization and then find factors of that happen to be perfect squares. So there is one funda about prime factorization of perfect squares that you need to know. What is that funda? What? Sorry. Power should be even. When you prime factorize any perfect square, each of the powers of each of the prime numbers has got to be even. In any perfect square, prime factorization, all powers will be even numbers. It's just that one little funda. You add that to this, you're done with this question. Prime factorization of a perfect square, every power on top of the prime, each of those will be an even number. So plug that funda and then you're done. We're going to discuss this one. 2 cube into 5 power 4 into 10 square into 3 cube. When simplified, it becomes 2 power 5 into 5 power 6 into 3 cube. So we want perfect square factors of this number. Any factor of this number will be of the form 2 power a into 5 power b into 3 power c. Now we know that a, b, c have to be even numbers. So the powers of 2 that we can accommodate are 0, 2 and 4. You can have 2 power 0, 2 square, 2 power 4. Powers of 3, 3 square, 3 power 0. Powers of 5, 5 power 0, 5 square, 5 power 4, 5 power 6. So 3 possible values on top of 2, 2 on top of 3 and 4 on top of 5. So total number of factors is 3 into 2 into 4 or 6 into 4, 24 factors. 24 factors of this number are perfect squares. What are those 24 factors? Product of all these numbers. If you multiply all of them and add them, then so the question asks for what is the sum of all factors of this number that are perfect squares. Then take this term, multiply that and find that. So that term you've got there 2 power 0 into 2 square into plus 2 power 4 into 3 plus 3 square into 5 plus 5 square plus 5 power 4 plus 5 power 6. Find that product. That will give you sum of all factors that happen to be perfect squares for this number. Product. It's going to be tricky. You have to find each and then think about how you can multiply. Or you have 24 factors. It's going to be tricky. You'll have to figure out some way of being street smart about it. You'll have to pair it in some way. I don't know how product can be. Let's discuss it at the end of the session, whether we can find product, but sum is simple enough. Finally, a very routine question. You'll get these as well. In your exam of 34 questions, at least 10 to 12 will be of the form where you know the formula, you plug it in, you get the answer. Not some fancy shortcut, not some really quick way of multiplying or dividing. Just one idea, one formula, plug it in, you're done. You should know the formula. Prime factorize this, plug into the formula, we're done for this. Prime factorize this number, we get 2 square into 3 into 7 into 11. So number of sum of factors is 1 plus 2 square into 1 plus 3 into 1 plus 7 into 1 plus 11. And so 7 into 4 into 8 into 12, whatever that number turns out to be. I'm not going to sit and multiply. You know the funda, you know the formula, plug it in. You should know the formula for finding sum of factors, product of factors, number of ways of writing a number as a product of two numbers, number of factors that happen to be even numbers, odd numbers, perfect squares, that happen to be multiples of some other number. All of these variants of that one formula you should know. And so every chance that you get a couple of questions in that, just nail that. You remember in this exam, you cannot afford to pause to think and figure out and all that. You see the question, you should know the method. At least for 25 out of 34. You should knock these down and then hope for the best. And so you should know this formula. You can't sit there and figure this out. Remember that. Yeah, should. Sorry? It says 2688 and 90. 2688 is it? We'll check that. Thank you. Yeah, it is not 2682. That is wrong. I'll check whether it's 2688. Find product of all factors of 324. Again, start with the prime factorization, then get to number of factors, number of ways of writing it as a product of two numbers, then build from there. Something funny about 324 as well. 324 is it's a perfect square. It's 18 square. Product of all factors of any number, nothing but the number raised to the power of half its number of factors. And so number of factors of 324. 324 is prime factorized as 2 square into 3 power 4. So number of factors is 3 into 5, 15. What does this mean? Of these 15 factors, you can take 14 of them and pair them up. And you keep on pairing them up. Each pair will give us a product of 324. So product of all of those is 324 raised to the power 7. So 324 raised to the power 7. At the end of it, we have an 18 left. So 324 power 7 into 18, or which is 18 power 14 into 18, which is 18 power 15. The direct formula, number of the product of all factors of n raised to the power number of factors by 2. And this works whether irrespective of whether n is a perfect square or not. That automatically gets adjusted. If n were not a perfect square, then we'll have an even number of factors. Everything gets paired up half the time, raised to the power 1 by 2, we're done. Right? If it has an odd number of factors, that means it has to be a perfect square. That means you leave out one. If it has 15 factors, you leave out one. You leave out the square root. The remaining 14 can be paired up. So you have 7 pairs. So it is 324 par 7 into 18. That 18 is still left, which is effectively 324 par 7.5. 324 par 15 by 2, which is 18 par 15. So product of all factors of n is n raised to the power number of factors of n by 2. That formula works whether n is a perfect square or not. It doesn't matter. Either way, that same formula works. Again, the funda behind the formula, know that because there's some small variant, you'll have to figure that mild variant out and then solve it. Always good to know some formula, know what sits underneath that. Try this one. In how many ways can 2520 be expressed as a product of two natural numbers where m and n are not coprime? Again, a good question, done in 2 steps. Those of you who know the method, keep plugging away. 2520, you know how to find number of factors. We also know how to find how many ways it can be written as a product of two numbers, m and n. Two natural numbers, m and n. Forget this coprime condition. We know how to find how many ways it can be written as a product of two natural numbers. We also know how many ways it can be written where m and n are coprime. You also know the formula for that. Subtract one from the other, you've got the answer. Find product of two numbers is 2520. Both are natural numbers. We know how to find that. Product of two numbers is 2520. Both are natural numbers that happen to be coprime. We know how to find that. Product of two numbers is 2520, where the numbers are not coprime. Subtract one from the other, you're done. Fine. So we know how to find how many ways it can be broken. We know how to find how many ways it can be broken when the numbers are coprime. So when they are not coprime, it's one minus the other. So you're going to do this in 2 steps. Have a go at that. Sorry, yeah.
So formula, it's 2 cube into 3 square into 5 into 7. So we can expand it. It's 2 into 3 into 3 into 3. So we have 6 multiplications to be done. 6.
Okay.
And we have to choose 2 out of those 2 to make it A and B. So can we use 6 either?
So you're writing it as 2 into 2 into 2 into 3 into 3 into 5 into 7. So basically saying I'll break it somewhere in between. It will not work. See, you can do that when the pieces are identical and you're allocating. When you do that, how will you aggregate 2 into 5 into remaining? In your list, there are 2, 2, 2, 3, 3, 5, 7. So you're saying it could be 2 into 2 into remaining. 2 into 2 into 2 into remaining. That's how you're breaking it. You're selecting some number in between, right? So how will you select a product where it is 2 into 5 into remaining, or 3 into 7 into remaining? That doesn't get counted. So the idea of saying, look, let me treat this as bars and pluses and symbols in between. If you're going by that approach, then what you're placing, everything has to be identical. They're all twos, all threes, all ones. Or you're taking a proxy for all twos, all threes, all one, all cars, all bikes, then you can do that. But if you're saying there are 2 twos, 3 twos, 2 threes, 5 and a 7, then you can't do that, because this 2 into 7 into the remaining, that cannot be aggregated. It is saying we want to find whether how many ways it can be expressed as a product of two numbers where the numbers are not co-prime. The number of ways of expressing as a product of two numbers, plug into the formula, number of factors by 2, 24, done. Number of ways where you can break it as a product of two co-prime numbers, how many ways are there? How many? 8. 4 primes, 2, 3, 5, 7, n minus 1 is 3, 2 cube, 8 ways. 2 power n minus 1, when there are n primes. The powers don't matter. Whether it's 2 cube into 3 square into 5 into 7, or 2 cube into 3 power 5 into 5 into 7, doesn't matter. The power doesn't matter. There are 4 primes, you're breaking them up. How many ways can you break them up into 2 parts? 8 ways, 2 cube. So 24 minus 8, you're looking at 16. So just listed down all the ways here. So 1 into 2, 3, 5, 7, 2, 3, 5 into 7, 2, 3, 7 into 5, 2, 5, 7 into 3, 3, 5, 7 into 2, 2 into 3 into 5 into 7, 2 into 5 into 3 into 7, 2 into 7 into 3. So totally 8 ways of breaking it as a product of two co-prime numbers. So out of 24, we strip out 8, we're left with 16 ways totally. And given number, you should know how to break it as a product of two natural numbers. Number of ways of breaking it as a product of two co-prime natural numbers. Number of ways of breaking it as a product of two natural numbers that are not co-prime. All 3. Fine. If you know 1 and 2, you know the 3. Fine. Let's go to the next one. This is a very simple question. You won't get a question like this. It's a good question because you're setting up questions that come further down the line. And so just knock it off. You will not get a question like this. And what's the answer? Fine. 36k plus 29 divided by 12. 36k is a multiple of 12. That goes off. 29 by 12, remainder is 5. And so obviously, this is too simple. So we'll go to the next one. Number n divided by 14 leaves a remainder of 5. What are the possible remainders when the number is divided by 42? How many possible remainders are there? 3. They are 5, 19 and 33. Keep jumping in steps of 14. At one point, one more leap will bring you back to the first number. 5 plus 14, 19. 19 plus 14, 33. 33 plus 14, 47, same as 5. We're good. And so these two fundas you should know. This one divided by 36, you know the remainder. Divided by 12, you know the answer. Unique answer. If you know remainder on division by 14, then on division by 42, there are 3 possibilities. Yep.
So like, is this 14 and 42? 42 is a multiple of 14.
Correct.
That's why it is fine.
Correct. Otherwise, we can't do this. If 14 and 42 were co-prime, then pretty much anything is possible. If they had a common factor, then you can take off that common factor and simplify. Then you'll get a narrower range.
Okay, if you're having 16 and 42, then you have to take out
the common factor,
and
then you simplify. There are many possibilities, but if 16 and 42, there are not 42 possibilities. That you can be sure of. But if it is 14 and 42, there are only 3 possibilities. But if it were 17 and 42, 42 possibilities are there. Everything is possible. The numbers are co-prime, everything is possible. When one is a multiple of the other, then there's narrow set of possibilities. If it is in between, then you have to narrow it down. So the possible remainders when you divide by 42 are 5, 19, and 33. Right? So this template is very useful. So why so? So if you divide a number by 14 and you get a remainder, then you can find one of three possibilities when you divide the same number by 42. If you divide a number by 3 and get a remainder, you can get one of 14 possibilities when you divide the number by 42. So what does this give us? If you want to find a remainder of a number when it is divided by 42, if you have the remainder when you divide by 14 and 3, you're good. You can combine in some form and get it. So in your exam, if you're asked for a question, it says, what is the remainder when you divide the number 44444 2017 times? When you divide by 55, you should say, look, I don't know anything about 55. I know I can find out when this is divided by 5, when this is divided by 11. So I can write this number as 5k plus something, 11l plus something. If I have 5k and 11l, I can combine to get 55m. That's the funda here. And so we will be doing a few questions of that template, but you're doing this exercise precisely for that. Some of you might have seen questions of this type under the category of Chinese remainder theorem. And so forget the terminology, the jargon. You don't need it. If you know the remainder when you divide a number by 6 and by 7, then you can find the remainder when you divide it by 42. If you know the remainder by 8 and 7, you can find the remainder when it's divided by 56. If you know 5 and 11, you can find the remainder when it's divided by 55. It's not just a product, but you list down these possibilities, those possibilities, find a meeting point, you're good. It's not the product.
So the numbers have to be co-prime.
If they're not co-prime, it will be the LCM. If you know the remainder when you divide by 8 and 6, you can find the remainder when you divide by 24, not 48. Same funda. 8 and 6 LCM is 24. If you know by 8, you know by 6, you can find for 24, not for 48. For 48, there will be two possibilities. Same.
48 you can do 2 and 24.
So you can't do 2 and 24. If you do 48, you will do 16 and 3. Right? So anytime you're trying to find, if you want to find remainder when a number divided by 48, find the remainder when it's divided by 16 and by 3, then combine these two. For 55, find by 5, find by 11, combine these two. Fine. It's not just the product, but you can combine those two. We're going to do one or two questions of that template also as we go further on. But precisely to do that, if they're doing this question. Otherwise, it's a very simple question. Divide by 14, you get the remainder. Divided by 42, you have three possibilities. Fine. So whenever you can narrow down possibilities, you can find, instead of dividing by 42, you can divide by 6 and 7 and then combine these two. That's the idea we are using.
Yes, like 6 and 7 because it is a co-prime.
They're co-prime. 14 and 3 will also work, but 14 is tough. 6 and 3 are simpler. Try this one. Sorry. Do all of you have the sheets with you? is a wonderful question because it's a very juicy, simple way of doing this. And there's another way where you can complicate it and simplify it. So I want you to find the simpler method. And you divide by 5, get remainder of 4. So this number is the form 5k plus 4. Divide by 6, get remainder of 5, 6l plus 5. 4a plus 3, 3b plus 2, 2c plus 1. And then you can combine them step by step, and then find. But this is a simpler method. And so if you rejig that way, it's far simpler. So try that. Give it a go. Another half a minute, and then we will discuss that. I'm going to discuss this one. So saying number divided by 5 gives a remainder 4. You can think of it as divided by 5 gives a remainder of minus 1. This number of the form 5k plus 4 or 5k minus 1. Either way it's the same. So the number is a multiple of 5 minus 1, a multiple of 6 minus 1, multiple of 4 minus 1, 3 minus 1, 2 minus 1. Effectively you're looking for a number that's a multiple of 2, 3, 4, 5, 6, and then subtracting 1 from that. That number will satisfy this condition. Fine. So the funda here, instead of thinking of it as 4, think of it as minus 1. Remainder of 4 on division by 5 is just minus 1 on division by 5. So this number is the form 2a minus 1, 3b minus 1, 4c minus 1, 5d minus 1, and 6c minus 1. Or n plus 1 is a multiple of 2, 3, 4, 5, and 6. Or n plus 1 is a multiple of LCM of 2, 3, 4, 5, and 6. LCM of 2, 3, 4, 5, and 6 is 60. So n plus 1 is a multiple of 60, or the number we are looking at will form 60k minus 1. So the number is 60k minus 1. You're looking at 119, and then going step by step from there. 119 plus 60, that plus 60, that plus 60. Or there are 900 3-digit numbers. You're looking at numbers that are 60 apart. 900 by 60 is 15. So we don't even care what the first number is, there'll be 15 numbers. And so you're adding in steps of 60, whether you start from 101 and add in steps of 60 or 145 and add in steps of 60, there'll be exactly 15 numbers. 900 is a multiple of 60. Each set of 60 will have one number that you're looking for. So 119 to 959. The textbook method is write down these numbers, treat it as an AP, find the number of numbers or count it in some form, all of that. But there are 900 numbers. You're going in steps of 60. No matter where you start, you'll have exactly 15 numbers. Any 900 consecutive integers will have exactly 15 numbers that are multiples of 60. So wherever you shift it out by, there are 900 numbers and you're counting in steps of 60. Wherever you start, there'll be exactly 60 numbers in that list. So exactly 15 numbers in that list. 115 to 959, 15 3-digit numbers satisfy this condition. So one funda is to count quicker. That is the last bit. The first idea, remainder of 4 on division by 5. Nothing but minus 1 on division by 5. So this number is the form 2a minus 1, 3b minus 1, 4c minus 1, 5d minus 1, 6e minus 1. Once you pick that, then it becomes far simpler. Otherwise, you'll have to do Chinese remainder theorem step by step, step by step. You'll get the answer as the number of the form 60k plus 59. Far easier to imagine it as 60k minus 1. Try this one. This is the funda we were discussing couple of questions ago. A number on division by 7 leaves remainder 3, divided by 9 leaves remainder 5. N by 7 gives a remainder 3, n by 9 gives a remainder 5. How many such 3-digit numbers exist? I'm going to give you the starting step here. N by 7 remainder is 3. So if you divide n by 14, you can get 2 possible remainders. N by 21, you can get 3 possible remainders. Right? Likewise, n by 9 remainder is 5. Then n by 18, you can get 2 possible remainders. N by 27, you can get 3 possible remainders. And so this number by 7 gives us a remainder 3. By 9 gives us a remainder 5. So any multiple of 7, you'll get a set of possibilities. Any multiple of 9 being the divisor, you'll get a set of possibilities. And so what is the divisor that we should choose? 63. So n by 7 remainder is 3. Find all possible remainders when you divide by 63. N by 9 remainder is 5. Find set of all possible remainders when it is divided by 63. Then think about combining these two. Or we could do it by the other method. Right? N by 7 remainder is 3, n by 9 remainder is 5. In both cases, the remainder is minus 4. So our number is the form 7a minus 4 and 9b minus 4. Which is form 63k minus 4. Simplify from there, you'll get the same answer. In our method, you have listed down numbers like 3, 10, 17, 24, 31, all of them. And from 5, we have written 5, 14, 23, all of them. Gone all the way till 59 and found that number. So our number would have been written as 63k plus 59 and then simplified from there. So it's far simpler. You'll get the number of the form 63k minus 4. So from 63 into 2 minus 4 to 63 into 15 minus 4, 14 different possibilities are there. And so I'm not doing that elaborate counting part. We're counting all numbers from 63 into 2 minus 4 all the way to the whatever the last possibilities, 63 into 15 minus 4. I'm not doing that part. 14 different 3-digit numbers are there. What's the answer? 0. And a proper freebie. 525 power 103. There's a 96 power 28. Multiple of 5 into an even number. 0. It's a wonderful question. It's a classic question. It's a wonderfully tough question. So take your time. Get this right. You want to find the smallest number that has exactly 16 factors. Try to find a number with 16 factors. And then we'll go to a variant of that number, smallest number, and the rest of it. Some number that has 16 factors. And then we'll work from there. And we want to find the smallest natural number that has exactly 16 factors. Once we find some natural number that has exactly 16 factors, we can work from there. Given a number, we can prime factorize and find how many factors it has. Given the number of factors, we cannot find the number, but we can possibly find the prime factorization. So find the underlying prime factorization that can result in 16 factors. And so, for instance, if you have a prime factorization that's p square into q cube, you still have 3 into 4, 12 factors. Not 16. I'm just writing down some number, some prime factorization, worrying from there. P square into q cube has 12 factors. And so find a prime factorization that will result in 16 factors and then work from there. The obvious prime factorization that has 16 factors is p power 15. That works. P power 15 has 16 factors. The smallest number of the form p power 15, 2 power 15. Right? So prime number power 15, 2 power 15. But we already know that you'll get a number better than that. We don't need to prime factorize it as p power 15. And so now the challenge becomes find all prime factorizations that can result in 16 factors. 16 can be written as 16. It can be written as 8 into 2. If you wrote it as 8 into 2, then you could have an underlying prime factorization, which is p power 7 into q. If you wrote it as 4 into 4, p cube, q cube. So find all those underlying prime factorizations that will result in 16 factors. And once you have done that, find the least possible number for each of those. And one of those is our answer. It's a classic question. It's a very tough question. You'll probably not get the number as high as 16, but 8, 10, 12 are par for the course. Now, smallest number which has 8 factors, which has 10 factors, those are very doable. 16 is tougher. Right? So, but the idea here is given that a number has 16 factors, what prime factorization could it have? That's a question. If a number has 16 factors, what could be its prime factorization? Not just one, I want all possible prime factorizations that will result in a number having 16 factors. We've discussed a few. P power 15 works, p cube, q cube works, p power 7 into q works. 16 can be written as 16, 2 into 8, 4 into 4. Anything else? P square, q square. Then will be 3 into 3 into 3 into 3 factors. PQRS will work. P into Q into R into S will work. So 2 into 2 into 2 into 2. Anything else? P cube into Q into R. So 16 can be written as 4 into 2 into 2. Don't just think of 16 as a product of 2 numbers. Think of it as a product of 3 numbers and 4 numbers. It cannot be 5. 2 power 4 is 16. So it can be written as a product of 2 numbers, just as one number, 16. 2 numbers, 8 into 2, 4 into 4. 3 numbers, 4 into 2 into 2. Sorry. And 4 numbers, 2 into 2 into 2 into 2. I can't even find where it is. So find the smallest possible natural number in each of these prime factorizations, and then we are good. Looking at p power 15, p power 7 into q, p cube q cube, p cube qr, or pqrs. And so P power 15, smallest number is 2 power 15. We don't even have to compute this. This looks like a giant number. 2 power 7 into 3 again looks large. 2 cube into 3 cube is 216. That works. That looks simple enough. P cube QR, 2 cube into 3 into 5. Obviously, you'll cube the smallest prime. 2 cube into 3 into 5 is going to be smaller than 2 into 3 cube into 5. So the larger power, stick it in for the smaller number. And simple idea. So 2 cube into 3 into 5 gives us 120. 2 into 3 into 5 into 7 gives us 210. Or the smallest number that has 16 factors exactly is 120. The number that can be prime factorized as P cube into Q into R, which is probably the most indirect prime factorization. If you're missing one, it's most likely that you've missed that one. Because breaking into two products, 8 into 2, 4 into 4, 16, that we'll get. 4 into 2 into 2. You can write 16 as 4 into 2 into 2. That underlying prime factorization gives us the right answer. So the smallest number that has 16 factors exactly is 120. Right? So do this as an exercise where you say I'll find the smallest natural number that has 2, 3, 4, 5, 6, 7 factors till 15 or 16. That exercise is very useful because it helps in one thing. Given number of factors, what could be the prime factorization? Given prime factorization, finding number of factors is easy. Given number of factors, what is the prime factorization possible? That is the other way around. That is a slightly trickier bit, but you get one round of practice for that, you're good. The previous question would have been too tough for cat. This one is very simple. Find the smallest number that has exactly 17 factors. I'm going to put some pressure on you. Answer? 2 power 16. 17 is prime. So it's only a number of the form P power 16 can give us 17 factors. Smallest number of the form P power 16, 2 power 16. Done. Try this one. This works up exactly the same idea. Number has 21 factors. What could be its prime factorization? That's all you need to crack. This number n square has 21 factors. What is the possible prime factorization that can result in 21 factors? What is the possible prime factorization? Sorry, P 3 into 7. So the prime factorization would be P square into Q power 6. The other one? P power 20. So this number could be of n square, could be of the form P power 20, or you could break 21 as 3 into 7. It could be of the form P square into Q power 6. So two underlying prime factorizations that n square could have. So key point here, you have 21 factors. So n could be of the form P power 20, or it could be of the form, P square into Q power 6. I'm still yet to get used to this digital pad. So P square into Q power 6, that results in 21 factors. P power 20, that results in 21 factors. And so now if n square were P power 20, then n would be P power 10. If n square were P power 6 into Q square, then n would be P cube into Q. Find number of factors for both of that, we're done. And so n square could be P power 20. That means n is P power 10. N square could be P power 6 into Q square. It means n is P cube into Q. Number of factors here is 11 factors. Here is 4 into 2, 8. Or n could have either 11 factors or 8 factors. How many factors might n have? Either 11 or 8. The key point here, find if the number of factors is 21, what could be the prime factorization? Once you crack that, you're through. Given prime factorization, finding number of factors is easy. Given number of factors, finding prime factorization is one layer tougher. There could be multiple possibilities. Find all of them. 3 numbers leave reminders 56, 51 and 49 on division by P. Sum of the 3 numbers leaves a remainder of 12 on division by P. Find P. So, good interesting question. Not just find P, find all possible values of P. Very vital. There is more than one value possible for P. I want both of them. Think about that. Should we discuss this one? So again, comes from just first principles. Number on division by P leaves a remainder 56. That number can be written as nk plus 56. Sorry, np plus 56. So just that, nothing more than that. So n1 is AP plus 56, BP plus 56, CP plus 49. If we add these 3 numbers, we should get AP plus BP plus CP plus 156. Remainders get added. We know that. So this number is a multiple of P plus 156, which is nothing but a multiple of P plus 12. We're told that sum of the 3 numbers divided by P leaves remainder 12. So remainder of 156 is same as remainder of 12. What does that mean? You add 3 numbers, the remainder should have been 156, but it's only 12. What does that mean? So, sorry? 144 is a multiple, so 156 minus 12 is 144. Our divisor is a factor of 144. So the number can be written as something into P plus 156. It can also be written as something into P plus 12. If you subtract one from the other, we know that P is a factor of 144. So our number can be written as Kp plus 156. It can also be written as Np plus 144. Sorry, Np plus 12. If you equate these two, then 144 is P times K minus N. Or our number P that we are looking for is a factor of 144. It could very well be 144. It could be 72. It could be 48. It could be 36. But can it be all of these? So what is the other condition? It should be more than the remainders. The largest remainder given is 56. So we're looking for a factor of 144. which also happens to be more than 56. So how many values are possible? 144 and 72. Two values are possible. And what we're looking for a number that's a factor of 144, which is also greater than 56. Should be greater than all the reminders. You cannot have a remainder greater than the divisor. So our number P should be factor of 144. It should also be greater than 56. Or we're looking for either 144 or 72. Only these two possibilities exist. So P is either 144 or 72. This is very similar to the previous one. Same template. Give it a go. Almost all reminders questions can be done with just that first principles idea. A number divided by d gives a remainder 28. That number can be written as kd plus 28. And so 5 times that number will give a remainder 5 times 28. 10 times that number will give a remainder 10 times 28. You can add two numbers, you can subtract one number from another, you can multiply two numbers. As long as the divisor is the same, dealing with the numbers or dealing with the reminders, this is the same answer. You can add two numbers and then take the remainder, or you can just add the two remainders. You can multiply two numbers and then take the remainder, or you can just multiply the two remainders. So number n on division by d gives a remainder 28. 5n on division by t should give a remainder of 140. 28 into 5 is 140. So we divide n by d, we get a remainder 28. 5n divided by d gives a remainder of 140. That's built in. This 140 is same as 8. So you should have got a remainder of 140, but as it turns out, this is just 8. Why has that happened? Because our divisor is less than 140. 140 is more than the divisor. So we divide 140 by d to get a remainder of 8. And so what does that mean? D should be a factor of 132. 140 minus 8 is 132. D should be a factor of 132. So it's either 132 or 66. That's it. That's it. 33. So 140, 132, 66, 44, 33. All four are possible. If you leave out one, you're walking into a wrong answer. And so the answer effectively is all factors of 132 that are greater than 28. Fine. So manually approaching is the best way. 144, 144 by 2, 144 by 3, 144 by 4. All four are higher than 28. 144, 66, 44, 33. Four numbers. We add all of them, we get one. This is more of a fun question. You're unlikely that we'll get a question like this. Give it a go. Give it a couple of minutes and we'll discuss this. So numbers of the form 11, 101, 1001, 10,001, they're wonderful numbers. So some of them are prime as well. Is 1001 prime? 1001 is 7 into 11 into 13. And you should know that You should just know that. So 1001, 1001, 1001. That's a funny number. So that's not prime. That much we know. It's a multiple of 1001. So it is 1001 into something. So the 1001 we know how to factorize. That is 7 into 11 into 13. So it is 7 into 11 into 13 into something. What is that something? 1 0001. So it is. If you have a 3-digit number, you multiply by ABC, you multiply by 1001, you'll get ABC, ABC. If you have a 4-digit number ABCD, you multiply by 10,001, you'll get ABCD, ABCD. A 2-digit number PQ by 101 will give you PQ, PQ. A single-digit number X into 11 will give you XX, 66, 77, 88, and all that. The same idea, which is extrapolating. Fine. So this is 1001, 1001. So this is 1001 into 10,001. That's a starting point. Any number of the form ABCD, ABCD is a multiple of 10,001. So this number is 1001 into 10,001. 1001 is not prime. Is 10,001 prime? That's the tricky part. So take some time.